Hi there, this is GCSE Waves Lesson 10 and this is Ultrasound Part 2. So ultrasound can be used to detect cracks or impurities inside materials or products. So as you can see in this image on the left hand side, you've got an ultrasound transmitter and receiver, and there's two scenarios. There's one on the right where the emitted ultrasound wave is going towards the end of the block and then reflecting back as normal. And on the left hand side you've got a wave that's traveling a shorter distance as it hits a crack, so it's causing an early reflection of waves. So this might be a good sample. So the first peak on the left hand side is the transmission, and the one on the right hand side is the reflection from the back of the block. A defective sample might look like this. So you've got the initial wave being transmitted, then you've got quite a significant wave there, which means that quite a lot of the ultrasound is being detected, so it's been reflected back. So that indicates that the crack could be quite severe, and then you've got some of the wave will transmit through the crack, hit the back wall of the block, and then you'll get that reflection as well. So we use ultrasounds to look at babies, prenatal scanning, or instead of babies, I should say fetus. So on a scan, you've got echoes versus time, which is typically what you'll get in your exam, and you'll have to do calculations off of it. We'll do some in a moment. B scan, lots of A scans all piled together, and then use a computer to compile an image to give a 2D picture. So there's an example. Ultrasound has been used to measure the thickness of the lens in a patient's eye. So 0 would be the initial transmission, 1. In fact, I'll let you have a think about it. So if you want to pause and see if you can figure that out before I explain it. Right, so the number 1 would be the cornea. So that'd be the first medium that it travels into. The front of the lens would be 2, and 3 would be the back of the lens. Alright, I want you to have a go at this one. Try this calculation, so if you want to pause, and then I'll explain how to do it. Right, so example, ultrasound has been used to measure the thickness of the lens. If each square is 5, that's mu, right, mu s, so that means microseconds. If you weren't sure about that, now you know. 5 microseconds, which means you need to divide it by 1,000,000, or do 5 times 10 to the minus 6. How thick is the lens? Speed of sound, this ultrasound is 1600 meters per second. So the answer is 4 millimeters. So what I'll do now is take you through that step by step. So number 2 is the front of the lens, number 3 is the back of the lens. So the thickness of the lens essentially is this bit here. So that's about 1 square. So that would be 5 microseconds. So distance is speed times time. In this case, thickness is speed times time. So speed is 1,600 multiplied by time, 5. You could do 5 divided by 1,000,000. But you'd be better off just writing 5 times 10 to the minus 6. So that gives us 8 millimeters. And then what we need to do, just like we did in the previous lesson, divide that by 2. Because essentially what we're doing is the exact same as what we did with the sonar questions. So we need to divide it by 2. And that gives us the 4 millimeters. Alright, let's continue. So there's some video links here. I'll put these in the description, so you can look at a fetus scan, dental cleaning, jewellery cleaning, ultrasonic radar, and ultrasonic testing. So they're all the things that we've discussed. So I'll put those links in if you want to have a look at them. Obviously feel free to do so. They're not my videos, but they are very good. Alright, let's move on. Right, so it's up to you what you do with this. You can write it out. It might take you a while, and then you can obviously link the application category used to and basic principle, or you could number them, or whatever it is. Right, okay, so I'm going to have a look at this one. So, removing kidney stones, that's a medical. So what we do is shatter the kidney stones, allowing them to be passed in urine, and the basic principle is energy in ultrasound waves used to break up the material. So let's look at the next one. So quality control, that's industrial. And we can use that to check for cracks in materials. We've just done a question on that one. And that's detection of reflected ultrasound to build up images. What about next one? Removing teeth plaque. So it's obviously medical. And it breaks up plaque deposits on teeth, and that principle is the energy in ultrasound waves used to break up materials. Submarine sonar. Military. That's to measure distances to objects or map out the seabed, and that's detection of reflected ultrasound to build up images. Prenatal scans, that's medical, and it's to image the fetus, and that's detection of reflected ultrasound to build up images yet again. And then last one, cleaning, which is industrial, and we can clean delicate instruments without dismantling them. So if you've watched those videos, you will have seen, or if you watch the video links after this, you'll see all those examples in real life. Right, so if you want to pause this and have a go at question 3 and 4, and then I'll take you through the answers. So a factory owner thinks a batch of syrup may be contaminated by shards of plastic. Describe how they could use ultrasound to check for this. So what you do is direct ultrasound waves at the tins. Ultrasound will reflect off each material boundary between the tin and the syrup. There'll be 2 reflection peaks produced. If the syrup is contaminated, you'll get extra peaks on your graph for each piece of plastic. So a proper one. Try to draw this really quick. Not very neat. The first one, if there's no issues, you might just get 2 peaks. If this is contaminated with plastic, you'll get reflection off of the plastic of the ultrasound. So you might end up with lots of little peaks. And you can see that that is indeed contaminated. So number 4, describe how a dolphin uses ultrasound to detect if a group of fish are getting closer. It says use a diagram like the one on the right, but I've not got a diagram. So a dolphin makes short ultrasonic click. You don't have to say click, but you could just say sends out ultrasound. Reflects off the boundary between the water and the fish, and then the dolphin simply listens for the echo. If the echo arrives more quickly, then the dolphin knows that the fish are getting closer. It's relatively straightforward. Exactly the same as sonar that a submarine uses. Right then, if you want to pause and have a go at this one. So a steel pipe was manufactured with a wall thickness of 4 centimeters. After several years of use, this pipe is tested for corrosion. A pulse of ultrasound is sent into the steel from the outer surface, and the reflection from the inner surface is detected. After a time of 5.1 times 10 to the minus 6 seconds, which is 5.1 microseconds, determine whether the steel is corroded at this point, and it gives you the speed of sound in steel, which is 5,900 meters per second. So what we need to do is calculate the distance for the ultrasound that's sent out after a time of 5.1 microseconds, and see if that gives us a distance of 4 centimeters or not. So distance travelled by the ultrasound, so distance is speed times time, so it's 5,900 meters per second multiplied by the 5.1 times 10 to the minus 6 seconds, and that gives you 0.03 meters. Distance to reflect an object, remember we need to half that, so that gives you 0.015 meters, which is 1.5 centimeters. And the pipe is corroded because there's a crack 1.5 centimeters into the 4 centimeter thickness of pipe. So that pipe has indeed corroded. Let's try one more. So I'm going to pause and have a go at this one. I've actually got the images here. Not my mistake on previous question. So number 6, a patient with a blood clot in his muscle. Obviously pause and have a go at this one. Is having an ultrasound A scan. On the display, P is one of the signal pulses produced by the transducer. Explain the origin of the pulses Q and R. So the transducer is what sends out the ultrasound, and then that's attached to the oscilloscope where we get our graphs from, like the graph below. The A scan, which has got the time on the x-axis. So Q and R would simply be reflections of the ultrasound wave pulse off the front and back of the blood clot. So Q will be the front of the clot, and R will be the back of the clot. So it says if each horizontal square represents 7.5 microseconds, how thick is the blood clot? Now this is a little bit tricky because Q and R is approximately a third of a square. If you didn't quite get a third, but you still did the technique right, if this was an exam question, there will be a range of answers. So peak separation is about a third of a square. So you need to do, obviously that's a time axis, so you need to do the 7.5 microseconds divided by 3. Which gives you about 2.5 microseconds, or 2.5 times 10 to the minus 6 seconds. I'll write that in. So it's 2.5, because this is what you'd use in your calculation. 2.5 times 10 to the power minus 6 seconds. So then it's just distance is speed times time. So distance travelled, speed times time. So it's 1,600 meters per second multiplied by the time, 2.5 times 10 to the minus 6, which gives you 0.004 meters. Then to get the thickness, we need to divide it by 2. So that gives 0.002 meters, which is 2 millimeters. So now, the technician or the doctor that's looking at this will know that the clot is 2 millimeters thick. Which doesn't sound very good. I've said before, I'm not a doctor. I don't have to give medication to break clots down or if they just remove it. But that's for them to worry about, not me. Right, hopefully that's helped. So that's ultrasound finished now. Thanks for watching, and I'll speak to you soon.